Namaste to one and all present here. I am Rajnish, a student of IIT Madras. On the behalf of Vande Mataram family, I would like to welcome our chief guest of the day, Professor Aditya Kolachana ji, to this session. I would also like to extend a hearty welcome to the faculty members, students, and other audience to the inaugural lecture of Vande Mataram for the academic year 2023-24. I request our chief guest to assume his place on the stage. Vande Mataram, our national song, embodies the historical culture legacy of our nation. Our national song has inherent nature which facilitates every Bharatiya to visualize and bow down in reverence to the divine maternal imaginary Bharat Mata and immerse everyone to perform their national duty. We have proudly followed the tradition of singing the national song Vande Mataram at the beginning of every lecture. Therefore, I invite everyone here to rise and join Ishanji to sing our national song. Hello.
Vande Mataram, Vande Mataram, Sujalam Sufalam, Malayaj Shitalam, Sashyashamala Mataram, Vande Mataram. Shubhra Jyotsna Pulakitayamini Pulak Sumita Drumadhara Shobhini Suhasini Sumadhura Bhashini Sukhadam Varadam Mataram Vande Mataram Vande Mataram.
Thank you, Ishanji. The Vande Mataram Forum at IIT Madras aspire to take initiatives that introduce and sensitize the student community about Bharat-rich culture, economical, socio-political, scientific, and technological heritage, its ramification today, and the thoughts about the roadmap ahead. The shloka from Ramayana, Janani Janma Bhumische Sarogadipi Gariyasi, which means that mother and motherland are superior to heaven, is the philosophy that has kept us going ahead for the last 8 years in this institute and strengthened our national consciousness. It gives me immense pleasure to welcome once again our guest speaker, Professor Aditya Kolachana ji, at the event. I request Professor Devendra Jalihal ji to welcome our guest by presenting him with a fruit basket. Thank you, sir.
Good evening, everyone. It's again honor and pleasure for me to introduce our distinguished chief guest of the event, Professor Aditya Kolachana ji. His journey through the academia and research. Am I audible, right? It's not working. Hello. Now it's better, right? So yeah, his journey through the academia and the research is nothing short of inspiring. Professor Aditya's initial academic journey started with Master of Science from IIT Kharagpur. He then pursued his MBA from IIM Ahmedabad and followed by PhD from IIT Bombay. What sets Professor Kolachana apart from not just his impressive academic credential, but also his remarkable research contribution. He has dwelled into diverse areas such as mathematics, astronomy, scientific literature in Sanskrit, and manuscriptology. His work has not only pushed the boundaries of knowledge, but also shed the light on Indian scientific heritage, in the recognition of his exceptional contribution. He has received the awards such as Young Historian of Science Award by the Indian National Science Academy and Award for the Excellence in PhD research from the IIT Bombay. Beyond his research, Professor Aditya is dedicated educator. He teaches two prominent courses in our Humanities and Sciences department, Astronomy in India and Maths in India. Having taken both of courses by myself, I can vouch for depth and the quality of his teaching. His passion for education recently earned him the Best Teacher Award for the excellence in teaching in year 2023. And I request everyone to reserve their question for the last Q&A sessions. And without taking much time, we will begin the session by hearing from our chief guest, Aditya Kolachana.
Thank you, Yash, for the kind introduction. Thank you. Good evening, everyone. So the topic of our talk today is the history of exact sciences in India. I have to be close to this. So it's not something which can be covered in 1 hour. It's a massive topic. In fact, as Yash mentioned, I teach 2 courses, Mathematics in India and Astronomy in India, and even 40 lectures in each is not sufficient to cover the full breadth of this topic. So at the outset, let me point out 2 more comprehensive sources if this talk generates interest. There is a fantastic 40 lecture NPTEL course called Mathematics in India, and in fact some of the points in this talk have been borrowed from there. So I would advise anyone who wants to do a deeper study of this topic can look up the excellent resource, the NPTEL course. So without ado, let me jump into this. The history of exact sciences in India. So mathematics and astronomy are generally referred to as exact sciences because you can state things with precision in these disciplines. In the Indian context, if we were to start out, I tell my students that our story begins with the Vedic literature, because that is when you are talking about the history of any discipline or any subject, you need to go back to the oldest available source. And in case of many disciplines, that is the Vedic literature in India. And the Vedic literature itself classifies knowledge into 2 categories. Okay. So in the Mundaka Upanishad, there is a classification of knowledge into 2 types, what it calls the Paravidya and the Aparavidya. So Aparavidya is stated to consist of the 4 Vedas, Rig Veda, Yajurveda, Samaveda, Atharva Veda, and what are known as 6 Vedangas, Shiksha, Kalpa, Vyakarana, Nirukta, Chandas and Jyotisha. And then there is also what is called as Paravidya, okay, Athapara Yaya Tadaksharam Adhigamyate, okay, that bit by which the immortal is known. So that's a whole different topic. We will not be covering that today. We will be sticking to Aparavidya, and the reason this has been stated is that it allows us to situate ourselves as to the position occupied by the exact sciences in India. So you can see that in addition to the Vedas, we have the 6 Vedangas. So these Vedangas are disciplines which are needed to be studied to actually properly interpret and understand the Veda. And one among these, as you can see at the very end, is Jyotisha. So what is this Jyotisha? Generally today people tend to have some perception about what Jyotisha means and whether it is scientific, unscientific. Let us go and look as to what Jyotisha is defined as. And Jyotisha, we will see, will broadly cover the disciplines of astronomy and mathematics. So much of mathematics in India was developed in the service of astronomy, at least in the initial stages. And so Jyotisha tends to cover astronomy as well as mathematics. So the Vedanga Jyotisha, the The Vedanga Jyotisha, there are several astronomical and mathematical references in the Vedic literature, but the first standalone work of astronomy in India is the Vedanga Jyotisha. And the Vedanga Jyotisha actually sets out the definition and the purpose of the text at the very beginning. So, Vedahi yajñārtham abhipravrittaha kalanupurvya vihitāscha yajñāha tasmādidam kala vidhāna shastram yo jyotisham veda saveda yajñāna. So, the Vedas have been revealed for the sake of performing the yajñas. And these yajñas have to be performed according to certain sequences of time. Tasmādidam kala vidhāna shastram. Thus, therefore, this Jyotisha is a science of time determination. It's being set forth to enable one to determine time precisely. So, Jyotisha is the science of time determination. Yo Jyotisham Veda Saveda Yajna. Thus, only one who knows Jyotisha can actually follow the Veda or follow the injunctions of the Veda precisely. So, this is the entire purpose of this entire science, at least in the initial days. And the Vedanga Jyotisha also states the status. What is the status of this discipline? This is a famous verse. Yatha shikha mayuranam naganam manayo yatha tadvad vedanga shastranam jyotisham murdhani sthitam. Just like the mayura is peacock, just like the combs of the peacock which adorn the peacock, and naganam manayo yatha, and the crest jewel of the serpents. Similarly, tadvat vedanga shastranam jyotisham murdhani sthitam. So, Jyotisha stands at the head of at the top of the Vedangas. So, this is the definition, the purpose, and the reverence in which this discipline was held. So, before we jump into some of the highlights, just a very broad overview of the development of these exact sciences in India. What are the major texts and how has it developed over the centuries? Like I mentioned, the Vedanga Jyotisha is perhaps the first text dedicated to the study of astronomy in India. And scholars have dated the recension which is currently available to us has been dated to about 14th to 12th centuries BC based on certain astronomical data available in the text. Another Vedanga, the Shulba Sutras, which comes in the Kalpa Vedanga, which is noted here. The Shulba Sutras are actually manuals for constructing the fire altars, which are required to perform the yajna as required in the Veda. And so this Shulba Sutras, various dates have been proposed. Usually the Bodhayana Shulba Sutra is considered the oldest of these, and some scholars have dated it to 800 BC or older, perhaps even up to 1000 BC. Probably the knowledge itself could have been older than that. These dates perhaps refer to the date of compilation of pre-existing knowledge into a dedicated text. Then we have Aryabhata. You would notice that there is a gap of about 1500 to 2000 years between Vedanga Jyotisha and Shulba Sutras and Aryabhata. It's not like there was no study in this time period. In fact, various texts note about 18 Siddhantas which existed before Aryabhata, but most of them have now been lost, probably because Aryabhata revolutionized the study of mathematics and astronomy in India. So that is the reason why 5 of these pre-existing Siddhantas were summarized by Varahamihira in this text called Pancha Siddhantika, which you can see here. So we get some sense of what existed before Aryabhata by studying Varahamihira's Pancha Siddhantika, which is only a summary and is not a reproduction of the earlier Siddhantas. Then there are several important scholars, some of whose names might be familiar and some of whose names unfortunately might not be familiar to many of you. So Bhaskara is famous for writing what is known as the Aryabhatiya Bhashya. It's a famous commentary on Aryabhata's Aryabhatiya and helps us understand in greater detail the intents and purposes of Aryabhata. Then we have the great savant Brahmagupta, who has written his main magnum opus Brahmasputa Siddhanta in the 7th century. We have a famous text by Lallacharya, Shishya Dhi Vriddhida Tantra. Up to this point, up to the 7th, 8th centuries, mainly these are all astronomical texts, and all mathematics is generally chapters within these astronomical texts. So the mathematics required to actually do the astronomy, mathematics tended to be chapters within this astronomical text. It's only around this period, Trishatika, Ganita Sara Sangraha, that we start to see standalone works on mathematics. Mathematics is started to be treated as a, separately from astronomy. It's still, I mean, a lot of the authors of these mathematical works tended to be still astronomers. Most of the names you see here are both, they are interdisciplinary, mathematics and astronomy, they tend to do both. So Mahaviracharya's famous text, Ganita Sara Sangraha, very famous text in mathematics. Then perhaps the most famous text in mathematics is the Leelavati of Bhaskaracharya, Bhaskara 2. And it has withstood the test of time, and even today it is considered to be a very good text on mathematics. In fact, it is still taught in some places today in India, the Leelavati. And then Bhaskara has also written Bija Ganita, which is a standalone work on algebra. And you can see, I will not go through the entire list. Okay, maybe I will just talk about Neelakantha Tantra Sangraha. Neelakantha is in the disciplic lineage of Madhava. So around the 14th, 15th centuries, for 300-400 years, mathematics and astronomy flourished in Kerala, what is present day Kerala, and modern scholars refer to that as the Kerala school. Perhaps I should have put one of the works of Madhava also in this list. I should have, but Madhava is missing here, but we will come to Madhava later on a little bit. Neelakantha has written the Tantra Sangraha. This is the text in which Indian astronomical tradition perhaps finds its finest expression, the Tantra Sangraha of Neelakantha. And the Ganita Yukti Bhasha of Jyeshtadeva, this is a major text containing several proofs and rationales for mathematical results as well as astronomical algorithms. Very, very important text. Generally, it's not well known that Indian mathematicians also gave a lot of proofs and rationales. So this is one text which is almost entirely dedicated to proofs and rationales. And perhaps one of the last major texts in this tradition is the 19th century text Siddhanta Darpana by Chandrasekhar Samanta from Orissa. So this is just a broad overview of the history and development of the exact sciences in India. And we will just look at a few highlights in the talk today, very few highlights in the talk today. Before I jump into that, just to again give you a sense, again I'm trying to make this more general interest rather than jump into all the technical things. What are these texts like? What are their contents? What do they discuss? How does it compare to, a textbook today? So we can get a feel for it. So for instance, if you were to look at an astronomical text, the Aryabhatiya of Aryabhata, so it has 4 chapters and 121 verses. So Aryabhata has dealt with mathematics and astronomy in just 121 verses to a fair extent. Okay, and I like to point out that, for instance, the Bhagavad Gita is 700 verses. So this is only 121 verses. So it's quite remarkable how Aryabhata has done it. So the first part is called the Geetika Pada. This is can be considered like a prologue to the text. It discusses a scheme of representing numbers. It defines some of the units of length and certain astronomical parameters which are required in the discussion in the rest of the text. So this is almost like a preamble, a glossary kind of a mixture of glossary and preamble, which helps to understand the rest of the text. Then the first chapter is known as Ganita Pada, which discusses, before you jump into the astronomy, you need to be equipped with certain mathematics which will help you understand the astronomy. So in the Ganita Pada, he discusses mathematics, squares, square roots, cubes, cube roots, properties of geometrical figures, construction of a sine table, how to go about constructing a sine table. Whenever I introduce this topic in my class, in my courses here at IIT, I ask students, if I took away your computer and calculator and your log tables, first of all, nowadays they don't even know what log tables are, but if I take it all away, could you reconstruct the sine table? And generally I don't get a very encouraging response to that question. There have been one or two folks who have answered and have come close to how it could be reconstructed, but it's very interesting. How do you construct a sine table? How do you construct it? So it's very interesting. And one of the very interesting things given by Aryabhatta is the solutions to first order indeterminate equations. So it's a non-trivial problem if the condition is put that you need an integral solution. So Aryabhatta is perhaps the first person to solve this, getting an integral solution to first order indeterminate equations. So that is one of the major contributions of Aryabhatta in the mathematics front. The third part is called the Kalakriya Pada, where this is now where you get into the serious astronomy. How do you compute planetary positions? There are certain models which are employed, planetary positions. So you need to first have a model of the universe. How do you imagine the motions of the stars and the planets, and then how do you compute their positions? So the celestial sphere and what are known as the eccentric and epicycle models, and what are the various calendrical elements. So as is clear from the name of the chapter, all these topics are discussed. And the final thing is called Gola Pada. Gola is literally sphere, and so the model of the universe which was adopted is that of what is called the celestial sphere. It's called the celestial sphere, and this part discusses the various aspects of the celestial sphere and the rules for various problems in spherical astronomy and various other computations of eclipses, etc. So this is just to give you. Later on, later astronomers have followed this model to a fair extent, but they have expanded it much more. So Brahmasputa Siddhanta of Brahmagupta is 1008 verses, and Vateshwara has written a much larger astronomical treatise, Siddhanta Shiromani, Tantra Sangraha. They are all much larger astronomical treatises which expand upon these topics in greater detail. And how does a mathematics text look? That is an astronomy text. So we said that from the 8th, 9th, 10th centuries, so on, independent standalone mathematics works started to be produced. And so perhaps the most famous of these is the Leelavati. And what are its chapters? So this also starts with paribhasha, terminology. So all the terminologies, what are the units of length, what are the units of weight, what are the units of volume. So because throughout the text, those terms, it will be assumed that you know what they mean. So he sets out the paribhasha first. And then you have what is called the parikarmashtakam. So 8 operations. So these are the basic mathematical operations: addition, subtraction, multiplication, division, square, square roots, cube, cube roots. And also the very first thing they set out is actually the place value system before you get into all this. So these are the operations which are discussed, and then how to compute, how to do these operations with zero, and how to do these operations with fractions. So all three they discuss Shunya Parikarmashtakam and Bhinna Parikarmashtakam. That's what they discuss. Then you can see that they have rules of proportions, quadratic equations, calculation of interest, how to compute when you have Mishranam, when you mix quantities, when you mix gold of various purity, how do you get it? What will be the purity of the resulting gold? Shredi Vyavahara, series and progressions. Kshetra Vyavahara, as the name suggests, it's all to do with geometry. This is the largest chapter usually in the mathematics works. Computing the areas, volumes, all those things are discussed. Khata Vyavahara, actually Khata Vyavahara is where the volumes are discussed. Chitta Vyavahara is the construction of altars, fire altars. Krakacha Vyavahara, so this deals with carpentry, sawing of wood. So the mathematics associated with the sawing of wood. So you might wonder what mathematics associated with sawing of wood. So the problem actually is, how does the carpenter determine his wages? Brahmagupta discusses this in more detail than Bhaskara actually. So how do you compute cross section of the wood, and then how do you determine the wages based on the area of the cross section and the hardness of the wood? So these are interesting discussion in this. Rashi Vyavahara has to do with computing the volume of heaps. So this appears to be targeted at solving a real life problem. So if you are a farmer in ancient or medieval India and there are no weighing scales, there is no way of easily determining how much is it that you have produced and how much should you sell it for. So these are some rules for, and I'm sure many of you are familiar that even today if you go to the villages, grains when the harvest happens are stored in heaps. So Bhaskara gives rules for quick computation of the volume of the heap, and depending on the kind of grain what formula should be used. There are some different formulae for different kinds of grains, and so you can easily determine, the farmer can determine the volume of their produce and probably then demand a fair price for their produce. Chaya Vyavahara is dealing with shadows. Kuttaka Vyavahara. So this is what Aryabhatta has discussed, but so these are solving this first order indeterminate equations, obtaining an integral solution. Bhaskara discusses it in far greater detail than what Aryabhatta has done. And the last chapter is known as Ankapasha, which is dealing with permutations. So before I move on, I'd just like to point out one thing here, that the text, the mathematics text, it appears to be aimed at, so Khata Vyavahara, the excavations, they generally discuss volumes in the context of excavations. So if you are building like the foundation for a building, or you are trying to excavate some, build a reservoir or a pond to store water. So all the computational volumes are discussed in that context. So what is evident from the Leelavati is, it is not, mathematics is not some abstract intellectual exercise. It is solving real life problems for various sections of the society. It is from a sociological perspective, it's a very interesting observation that it is a text. By the way, this is a Sanskrit text, and it is intended to address problems in various sections of the society. So generally there are some misconceptions about both the authors and the intended audience of these kinds of texts, but it's very clear. There's no point having sections on Rashi Vyavahara, Krakacha Vyavahara, Khata Vyavahara if it is not going to be applied in those areas. Okay, so few highlights. Okay, so I will not take too much time. So if we start with the Vedic literature, it's very interesting. So there is this passage in the Taittiriya Samhita of the Krishna Yajurveda. So Shata Yaswaha, Sahasra Yaswaha, Ayuta Yaswaha, Niyuta Yaswaha. Powers of 10 from Shata is 100 to 10 power 12 are very explicitly stated in the Yajurveda. And we also find, what basically we observe is that there are several passages in the Vedic literature which seems to indicate the decimal system being in vogue, the base 10 system being in vogue. So this is the powers of 10 which are explicitly listed. And then there is this famous passage again from the Taittiriya Samhita, Yajurveda, Ekacha me, Tisrascha me, Panchacha me. So this is all the odd numbers are listed from 1 to 33. And then multiples of 4 are also there. Chatusrascha me, Ashtaucha me, Dvadashacha me. So 4, 8, 12, so on until 48. So there are several such passages. In the Rig Veda also we find, let me skip that. There is also some interesting number 3339 which appears in the Rig Veda, which Professor Iyengar has shown that it has some significant astronomical significance. It's very interesting, but I will not, due to paucity of time, I will not get into that. And then in this famous verse, Purnamadaha Purnamidam, that also seems to indicate certain notion of infinity. Purnamadaha Purnamidam, that is infinite, this is infinite. Purnat Purnamudachyate, the infinite comes from the infinite. Purnasya Purnamadaya Purnameva Avashishyate. When you take out the infinite from the infinite yet remains. So it's a very, very interesting, both from a philosophical and a mathematical perspective. what is very interesting is how much math is there in non-mathematical texts. How much math is there? In fact, one of the best definitions of or the descriptions of the place value system is found in the the commentaries to the Yoga Sutras of Patanjali. So, Yathaika Rekha Shatasthane Shatam Dashasthane Dasha Ekacha Ekasthane. So, he uses the place value system as an analogy to explain some other concept. So, and similarly, Shankaracharya in his Brahma Sutra Bhashya also employs the decimal place value system to explain another concept, which seems to indicate that this was something which was very well known in society. If you are trying to explain some difficult concept in yoga or philosophy using the place value system, that seems to indicate that this was widely known in society. So that's an interesting observation that we find. And even the one this use of zero we do find in various non-mathematical contexts. We find it in the idea of a null morpheme in the Ashtadhyayi of Panini, Adarsham, Lopaha. It is found in a text on prosody, the Chanda Shastra of Pingala, where he is giving an algorithm to compute the powers of 2. Rupe Shunyam, Dvish Shunye. This is an algorithm, this is an efficient algorithm to compute powers of 2 without having to, if you want to compute 2 power n, you can multiply 2 n times. But this reduces the number of steps in this algorithm of and then of course in various philosophical traditions there is this concept of shunya or abhava in various philosophical traditions as well. So one of the fundamental problems of astronomy, you want to do anything in life, you have to first find the directions. You want to construct a house, you want to perform a yajna, you first need, because everything needs some alignment. Even today we first figure out what is the direction. And this problem has been solved. It's a non-trivial problem actually. So when I ask my students in the class, how will you find east? So the first answer I get is, we will get up in the morning and look at the sun. So I'll be like, I'll be very happy if you get up in the morning to look at the sun. But that's not going to give you east. That's not going to give you at least the exact east. And so it's and they have come up with a beautiful technique in the Shulba Sutras to find exact east. All it requires is a stick and a rope. And this again, I like to tell this my students, that a lot of math was done with just a stick and a rope. With just a stick and a rope. So perhaps without getting too deep into the method, you just you put the stick perpendicularly on level ground, you draw a large circle around it, and then you note when does the tip of the shadow enter the circle in the morning. It will initially be outside. Note it when it enters, the tip is on the circle. And then in the afternoon, as the shadow lengthens again, note when the tip just touches the circle and is about to go out. And when you join those 2 points, you will get east-west. So this is the procedure prescribed in the Shulba Sutras. And later astronomers, so the students who have taken my astronomy course know that this entails a small error. And later astronomers have actually shown what is the error and how to adjust for that error as well. So very interesting, and this goes as far back as the Shulba Sutras. And the commentators actually note the same doubt which the students have. Why cannot I just look at the sun in the morning and find east-west? And so they note that the sun rises at different points on the horizon over the course of the year. So you cannot, except on the solstitial days, except on the equinoctial days, you cannot find exact east by looking at where the sun is rising. So again in the Shulba Sutras, we find a very clear enunciation of the so-called Pythagorean theorem. So this is known as the Bhujakoti Karnanyaya in India. In fact, I was very pleased in one of my classes a couple of years ago. So one student told me that he had studied in Hindi medium school, so he knew what was the term in India, whereas everyone else had only heard the term Pythagoras theorem. So this Dirgha Chaturashrasya Akshneya Rajjuhu Parshvamani Tiryangmani Chayat Pratak Bhute Kurutah Tadubhayam Karoti. So this is the statement. Let me not get into all the Sanskrit and the definition of it, but it says that the diagonal of the rectangle will do what the base and the height do. And the very next sutra actually lists out various triples. Various triples are listed out. Trika Chatushkayoho, Dvadashika Panchikayoho, Panchadashika Ashtikayoho. So 3, 4, 5, 12, 8, 15. All the Pythagorean triples are listed in the very next sutra. And there is an even more explicit statement in one of the other Shulba Sutras. I'll just perhaps. What is very also interesting is there is a approximation for root 2 in the Shulba Sutras. Very interesting. Pramanam tritiyena vardhe taccha chaturthena atma chatustrim shonena savisheshaha. So basically this is the sort of rational approximation to root 2 which is given in the Shulba Sutras. And there are several ways. We don't know how they came up with it, but you can basically take two squares, cut it into various parts, put them back together and try to arrive at this expression. Again, due to paucity of time, I will not jump into all this. So now I will come from Shulba Sutras, we will come to Aryabhata. So Aryabhata, so we will look at some very interesting astronomical concepts which Aryabhata has stated far ahead of his time. So he says, Vritta Bhavanjara Madhye Kakshya Pariveshtitaha Khamadya Gataha Mrujjala Shikhivayumayo Bhugolaha Sarvato Vrittaha. So he is basically stating that the earth stands supportless in space at the center of the circular frame of asterisms. So this is the concept of the celestial sphere. And Bhugola, it's very interesting that earth is referred to as a sphere very explicitly. And it is surrounded, it is made up of water, earth, air and fire and is spherical. And in the very next verse, he likens the earth to a Kadamba flower. So those of you who know or don't know, I suggest you Google it. The Kadamba flower is a globular flower which has blossoms on all sides. And so he compares the earth to the flower and he says that the blossoms of the flower are like the terrestrial and aquatic living beings surrounding the earth on all sides. So it's a very, very beautiful comparison that he carries out in the Aryabhatiya. An even more interesting observation that he makes is he compares the motions of the stars in the sky, the motion of stars in the sky. So he says, just like a person going in a boat, anuloma gatir naustha pashyat achalam vilomagam yaddut. Just like a person going in the boat observes the fixed objects on the banks to be moving backwards. Achalani bhani tadvat. The stars are also to be considered to be fixed like that, and our observation of their motion is actually, it's we should consider that to be similar to the objects on the bank of the river. That means they are actually fixed and we are the ones who are moving. We are the ones who are rotating. And then he goes on to state that so this whole rising in east and setting in west, it is comparable to this objects that are observed on the motion of the bank, objects on the banks of the river. So it's a very, very interesting, so this was far ahead of his time, and it's a very interesting statement. And then many people are surprised to know this, but Indian astronomers have very clearly defined a prime meridian for all their computations. And Aryabhata, so even the Surya Siddhanta discusses it, and Aryabhata also discusses it. Sthalajala madhyal lanka bhukakshyaya bhavet chaturbhage ujjayini lankayah tachaturamshe samottarataha. So he clearly states, so Lanka is the technical term they use for the Earth's equator in Indian astronomy. And so he says that the prime meridian passes through Ujjaini, and that will be 1/4 of a quadrant from the equator. 1/4 of a quadrant is 22.5 degrees. So he is basically giving the latitude of Ujjain as 22.5 degrees, which if you go and check will be fairly there. It's fairly accurate. So the prime meridian is that which passes through Ujjain, which is at a latitude of 22.5 degrees. So this is what Aryabhata states. And his comment, Bhaskaravan in his Laghu Bhaskariya, he gives even more explicit statement of the prime meridian. Okay, Lanka Vatsyapura Avanti Sthaneshwara Suralayan Avagahya Sthita Rekha Deshantara Vidhaini. So what the line which passes through Lanka, Vatsyapura, Avanti, Sthaneshwara and Meru. So Lanka here refers to the intersection of the prime meridian and the equator. So the 0, 0 point. So Lanka, Vatsyapura has been identified, some scholars identify it as a place in Karnataka. Avanti is of course another name for Ujjain. Sthaneshwara is currently it's known as Thanesar in Haryana. And Meru, Suralaya is the North Pole. So this is the prime meridian, very explicitly stated by Bhaskara one. So, and all computations, unless otherwise stated, are assumed for Ujjain in Indian astronomy. And then you need to employ what is known as the Deshantara Samskara. So that is why it is called the Deshantara Vidhayini in this verse. So you have to correct for longitude with respect to Ujjain. Another interesting verse which comes in Bhaskara's Siddhanta Shiromani, Bhaskara states, Akrishta Shaktischa Mahi Tayayat Khastam Gurum Swabhimukham Swashaktya. So he says the earth has a power of attraction due to which all objects fall down. And then he says, that being the case, and it's uniform all around the earth, he says, and this being the case, so he's also trying to make a point about the earth being supportless in the sky. And then he says, if it were to fall, where would it fall? Everything actually falls onto the earth. So that is the kind of statement he is trying to make. There is a wider context to it. I will not get into that now. Why they are trying to prove that the earth is supportless in space, there is a wider context to it. Okay. I'm just jumping, okay, because we don't have time. I'll just, in the highlights part, I will just conclude with this one verse of Madhava, which is perhaps not very well known. I also actually want to cover a little bit of the pedagogy and a little bit of proofs. That's why I'm just jumping. So this is the famous infinite series for pi given by Madhava. Vyase varidhi nihate rupa hrite vyasa sagara abhihate Trisharadi Vishama Sankhya Bhaktam Runam Swam Pruthak Kramat Kuryat. So it's quite remarkable that, so this is the expression, it's in effect it is stating pi by 4 is 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 so on unto infinity. And in beautiful Sanskrit verse, so Vyasa is the diameter. So basically this is being stated as a relation between the circumference and diameter of a circle. So Vyasa is the diameter. Vyase Varidhi Nihate. Varidhi is ocean. Ocean represents 4 in what is known as the Bhuta Sankhya system. So 4 times the diameter, Rupa Hrite divided by 1 and so on. You divide Trisharadi Vishama Sankhya Bhaktam Runam Swam Pruthak Kramat Kuryat. So you have to divide by odd numbers and alternately subtract and add. So this is stated to be the circumference, so which is nothing but the so-called Gregory-Leibniz series. So this is about 2-3 centuries before. So this is the beautiful expression. So I have just given some highlights of astronomy, some highlights of mathematics. What I want to spend some time is on the pedagogy, because it is truly remarkable. Generally we get caught up in the results but don't really appreciate the pedagogy. And perhaps the best example of mathematical pedagogy is the Leelavati of Bhaskara. And maybe I'll just share a couple of verses. And this is particularly, we have unfortunately lost this pedagogy in India today. But in my opinion, it has great value, particularly for taking these subjects. There is a lot of fear for math in a lot of students. I'm sure it's not problem familiar here in this room. But so just to give an example as to how Bhaskara, for instance, states the root for the quadratic equation. So I remember in school, we remember minus b plus minus square root of b square minus 4ac by 2a. Maybe we didn't face much difficulty in memorizing that, but I'm sure you all had friends in school who would fear mathematics like anything. So now imagine that instead of trying to memorize that, that scary formula, you did it this way. Gunaghnamulo na yutasya rashehe drishtasya yuktasya gunardhakritya मूलं गुणार्धेन युतं विहीनं वर्गीकृतं प्रष्टुरभीष्टराशिः. Okay, believe it or not, it gives the same formula. Believe it or not. Okay, so this is in a poetic meter called Upajati. So Bhaskara is the hallmark of science in India is most of them were not only great scientists but also great poets. They were also great poets, and Bhaskara was certainly poet par excellence. So this is a beautiful, again, we don't have time, but it's very beautiful how the result can be. And the advantage of a system like this is, you don't have to scare the students first of all by putting all this square roots and variables and all. You are just first teaching some melody to the students, some poem, and you don't even have to, initially the meaning can come later. You first enjoy it, and slowly as you hum it in your mind, and the teacher then can slowly reveal the meaning in a non-threatening way. So it's a very remarkable approach which we have unfortunately lost, and some attempts are being made to revive it. We really need creative mathematics teachers to take something like this forward. And so just to give you again how examples are set. So this is in a beautiful verse in what is called Shardula Vikriditam. The meter is called Shardula Vikriditam. Yatam hamsakulasya moola dashakam meghagame manasam प्रौढ़ीय स्थल पद्मिनी वनमगात अष्टांशकोम्भस्तटात बाले बालमृणालशालिनि जले केलिक्रियालालसं दृष्टं हंसयुगत्रयं च सकलां यूथस्य संख्यां वदा. Okay, so this is, believe it or not, this is a problem in quadratic equations. He is posing a problem in quadratic equations with this. It's in effect this problem. And you have to state the result. What is it's a problem involving swans, and there is such evocative imagery. There is this herd of swans, okay, and the rainy season is approaching, and so they are deciding to migrate. And so some of them go to the Mansarovar lake, some of them go to what is known as the Thalapadmini forest, okay, and there are 3 laggards. Okay, everyone else has migrated. These people are somewhat lazy and they are still playing in the water. Everyone else has gone, they are still there only. So it's such evocative imagery, and I mean, who will not enjoy math if it is taught in this way? So this is a beauty. And just to another example, this is the famous battle between Arjuna and Karna, and he weaves a problem in quadratic equations using that battle as an example. Partah karnavadhaya marganaganam kruddhorane sandadhe tasyardhena nivarya tacharaganam mulais chaturbhirhayan shanlyam shadbhirateshu bhistribhirapit chatram dhvajankarmukam chichedasya shirasharena katite yan arjunas sandadhe. Okay, so Arjuna has some unknown number of arrows, and some of them he uses for various purposes for various parts of Karna's chariot and the Sarathi, and ultimately one for Karna himself. And so how many arrows did Arjuna have? So you can also see that it is not only the pedagogy is very, very pleasing, it is also rooted in familiar culture, which clearly, so this is an incident which is an event in the Mahabharata, a story from the Mahabharata, almost every kid will know. And when you weave an example around that, it immediately generates interest and enthusiasm and motivation. So again, this is perhaps a art which has been lost and has to be revived. So there are, I mean, if I get into the Leelavati, we can go for hours and hours, but I will not spend time. Just one example in combinatorics. Pashankushahi dhamaruka kapala shulaihi khatwanga shakti sharachapayutair bhavanti anyonya hastakalitaiः katimurti bhedaः shambhor hareriva gadari saroja shankaiः. So he's saying Vishnu has 4 hands, and then there will be some 4 items in the 4 hands. So how many possible idols of Vishnu can you make? Okay, by interchanging the items. And similarly, Shiva has 10 hands. Okay, and they have Pasha, Ankusha, Dhamuru. So there are various items. So how many various different idols of Shiva are possible? So the answer will be 4 factorial and 10 factorial. And again, it's a very imaginative way of posing the problem. So if we have time, so I will just perhaps conclude with a few examples of proofs which are present in. I will not go into any difficult proofs here, that they will also take time. Some simple proofs which have been discussed, because this is not a well-known thing that Indian mathematical texts have also discussed proofs. So we will consider proofs from a text called Nisrushtartha Duti. This is a commentary on the Leelavati which we have just seen. And Nisrushtartha Duti means, Nisrushtartha means the intended meaning or the bestowed meaning. And Duti, Duta you know, is the messenger. So the messenger of the intended meaning. That means the commentator is stating that don't worry if you don't understand the main text. I will convey the intended meaning. There will be no interpolations and errors. Whatever is intended will be faithfully communicated to you. Will be faithfully communicated to you. That's what it is. They came up with very creative names for the texts. Very, very creative names. So I think one of my favorite names I always point out in the class is, we saw one of the texts was of Lullacharya was called Shishya Dhi Vriddhita Tantra. Okay, so the text which enhances the intellect of the student. So they came up with very interesting names. Okay, so before we jump into the proof, again I will just state the verse in the Leelavati on which the commentator is trying to give the proof. So these are 2 verses which state various summations. So this is in a meter called Dodhakam, beautiful meter employed by Bhaskara. So this goes something like this. So this basically, this verse states these 2 relations, the sum to n terms and the sum of sums. So which most of you would have studied in school. Sum to n terms is n into n plus 1 by 2. And then the sum of sums is n into n plus 1 into n plus 2 by 6. And so these 2 results are stated this way. Saika padagna padardham athaikadyanka yutih kila sankalitakya sadviyutena padena vinigni syatrihrita khalu sankalitakyam. Okay, so sankalita is the term they use for summation. So I will skip that, and then in the next verse again in the Dodhakam he gives the results for the sum of squares and sum of cubes. So I will jump the proof for the sum to n terms. It is he discusses 3 different proofs actually, very interestingly, including one of the standard proofs where you write 1 to n and then you write it in reverse, you sum them and divide by 2. Even that proof is given, and then he gives a couple of other proofs also, interesting proofs. When I ask students what is the proof for the sum of sums, I am very surprised that almost no one tends to give me either the proof for sum of sums or the sum of squares. IIT students, I find it very surprising. And so then I share, okay, let us see what Munishwara has done in the Nisrushtartha Duti. So the sum of sums, the proof for the sum of sums is very elegant. So what Munishwara states is, you list all the sum of sums. So sum of sums is, so in the first row you have sum to 1 term, in the second row you have sum to 2 terms, third row you have sum to 3 terms, and so on till sum to n terms. So the problem is now you have to sum all these sums. And so the approach given is sum them by column. Okay, sum them by column. That is the approach which is given. So you will have n times 1 plus n minus 1 times 2, n minus 2 times 3, so on until you have n minus 1 times n. And then some further manipulation is given and they arrive at the result. It's a very interesting proof which is there. Similarly, sum of squares also, it's very interesting. There seems to be this graphical component. In fact, Neelakantha has given how this proof can be given in geometrically. It's very interesting. But there seems to be always a visual, graphical component to the proofs which make things very clear in the student's mind. So how do you come to sum of squares? Similarly, you list out all the squares. So 1 square is 1 listed once, 2 square is 2 listed twice, 3 square is 3 listed thrice, and so on, and n square will be n listed n times. So again, the method is sum by columns. Okay, so the first term is sum to n terms. The second column is sum to n terms minus sum to one term. The third column is sum to n terms minus sum to two terms. And then you do some manipulations. He talks about how you manipulate that and you arrive at the result. So it's a very, very interesting proof. And very interesting proof for sum of cubes. This is actually the easiest of the proofs. And I have never so far, none of my students have been able to actually, when I ask them how do you give the result for sum of cubes, I have never got the answer in class. So there is a very simple observation they make, okay, that you take the square of the sum to n terms and the square of the sum to n minus 1 terms, their difference is n cube. Their difference is n cube. And so that's all. You have the result immediately. So if you have the summation of cubes, 1 cube can be written as the square of sum to 1 term minus square of the sum to 0 terms, and so on. All the terms will cancel out and you will only have the square of sum to n terms remaining. So it's a very, very interesting proof which is given in the Nisrushtarthaduti. There are even more sophisticated proofs for more complex formulae. So for instance, we saw Madhava's infinite series. It's a spectacular proof in the Ganita Yukti Bhasha, but we don't have time for that. That will be a very long proof. So I will just, so this is a snapshot of the manuscript, the proofs that we just saw from the Nisrushtarthaduti. I just want to conclude on this note with that it is again not well known. It is not known that Indian mathematicians gave proofs. It is almost, no one knows that they made extensive use of algebraic notation in their discussions. We generally tend to think of algebraic notation as some that we have learned from Europe, but Indian texts are full of algebraic notations. This is just one example. So for instance, if you look at this expression here, per gha 1, per va 3, per 2 by 6. So per is the term they use, pada, to indicate the number of terms. So this is equivalent to the n that we are using in our formula. And per gha indicates ghana is cube. So per gha is nothing but n cube here. And 1 is the coefficient which comes actually in the Indian system, it comes after the variable, not before the variable. So per gha 1 is literally 1n cube. Per va 3, pada varga is square. So this is 3n square and then 2n divided by 6. So this is the formula stated in notational form. So this is, so I'll just now conclude. So what is the takeaway we should have? India has had a continuous tradition of exact sciences spanning several millennia. And so we have seen Vedanga Jyotisha Shulba Sutras up to very recent times. There have been numerous texts and numerous scholars who have contributed to various aspects of mathematics and astronomy. And so they have made important contributions to the advancement of their disciplines. And the Indian mathematical and astronomical texts do not merely state results but also contain detailed proofs. This is an important takeaway. And the poetic pedagogy made science and mathematics more accessible to the lay public in an engaging manner. And finally, the mathematicians and astronomers have applied their skills to address the needs of various sections of society. It was not a abstract, intellectual exercise. It was solving societal real life problems. So with that I will conclude. Thank you.
Thank you, sir. It was indeed a very insightful instruction. The information you presented enlightened us on the topic. Now we shall have a brief Q&A session. I request the audience to introduce themselves and limit to one question in the interest of time.
Good evening, I am Tejas Joshi, and my question is that I have read that the text Leelavati, it actually enables you to count the number of leaves on a tree or something like that. I have read on a tree. I have read something about that. So is it really true or is it just a legend?
So I am not familiar with that legend. There are other legends associated with the Leelavati. But most of the legends associated with the Leela, I mean, there is one famous legend associated with the Leelavati, but which scholars have shown that probably was a later interpolation about his daughter and that whole legend. I have not heard of this particular story about the Leelavati, but it does contain, we have seen the contents of the text. It contains everything from the basics to first order indeterminate equations. So I am not sure if that will help in counting the number of leaves.
So is it rather rigorous than mystical or something like that?
Yeah, it's a very
structured
and proper mathematical text.
Yeah.
It's just that it is in a the pedagogy is poetic, that's all.
Yeah.
Otherwise it's a proper mathematical text.
Yes, thanks.
It's very precise also. It's a very precise text.
So basically I have two questions. The first one being, like among all these mathematical operations that we see, is there something that our modern mathematicians have yet not encountered and it is still present in the text?
Okay.
Like it is about discovering an unknown knowledge. That's question number one. And question number two would be like, is there a reference to differential and integral calculus? What I've heard from other sources that the Kerala school of mathematicians have worked upon that on the same year as what Newton did it. Is it true?
Yeah. So I wouldn't say that. See, mathematics is a very old science. Okay. I wouldn't say that there is anything in that sense, some undiscovered math, some stunning result or formula which was unknown before. At today's date, I don't think we can say that at today's date. But what is certainly unique and stunning and unattempted anywhere else is the pedagogy, as I mentioned. It's a very unique pedagogy, which seems to be very unique in the Indian tradition, and even in the Indian context, Leelavati is a class apart. So that is the answer to the first question. And with regards to calculus, yes, the Kerala school have certainly made several. In fact, we saw Madhava's infinite series for pi, and the way they give the proof, if we look into that, that will be actually summing up of infinitesimals, the way they arrive at that result. Even Bhaskara has used differential calculus in the sense that they use in the astronomical text, in Siddhanta Shiromani and some other Kerala school texts, we come across this concept of Tatkalika Gati. So instantaneous velocity, and they have actually given the expression of the differential in those texts. So I suggest that you watch two videos of the NPTEL lecture, Calculus 1 and Calculus 2, you will get more information on this.
I'm Himanshu, a research scholar in the Department of Mathematics.
Okay.
Sir, how do you see mathematics either as a science or as an art? And my question is supported by the fact that few years back, all the educational institutes of India used to provide the degree BA Mathematics Honours, MA Mathematics Honours, and suddenly they changed to BSc Mathematics Honours, MSc Mathematics. And I also want to know the change behind this.
Okay. Is it? See, the Indian mathematicians saw no dichotomy in that. Okay, it was both art and science for the Indian mathematicians for sure. And it was not just mathematics, but all scientific disciplines tended, whether it was Rasayana or astronomy or linguistics, they tended to, a lot of Ayurveda, medicine, it was all stated in, they combined both art and science. I don't think in the Indian context this were looked at as very separate entities. That is the best I can answer that question. And as to the why BSc Mathematics Honours and all, I am sorry, I have, it's not my, I have, believe it or not, I have never studied in a mathematics department, so in all my degrees, so I will not be able to answer that.
My name is Jay Shankar. And sir, my question is regarding the manuscript. There are two questions, they are very linked. Firstly, regarding vernacular texts in languages other than Sanskrit, and mathematical texts and astronomical texts discussing the things that we spoke about. And secondly, the question related to it, were these texts passed on through manuscripts, or were they passed on like the Vedas, the Shruti Parampara that we have?
Okay, so there are certainly several texts in mathematics and astronomy in languages other than Sanskrit. So for instance, one of the first texts in Telugu, first mathematics text in Telugu is called Pavuluri Ganitam. But that happens to be actually a Telugu translation of Ganita Sara Sangraha. Similarly, in other languages also, Leelavati for instance has been translated into many languages. Generally, at least what I have noticed, actually not much work has gone. See, not much work has gone even into Sanskrit texts. So leave alone non-Sanskrit texts. So generally, as of now, the focus appears to be in Sanskrit texts, but not much work has really gone into. There are people who are working on some texts which are available in Tamil also. There are certainly texts which are available, but a lot more research has to be gone. So I am not fully qualified to explain the extent of what is available. As far as I am aware, there are only a few so far, but even in Sanskrit, many things are being discovered by the day as people go and spend time in manuscript libraries. What was the second question? How is it passed on? See, in the initial days, it was certainly, so there are two types of texts, what are known as the primary texts and the commentaries. The primary texts tend to be in verse and are probably meant to be studied and memorized orally because they help you. We memorize formulae even today. Memorizing it by verse is just a more efficient way of memorizing the formula. So they were probably intended to be memorized, whereas the commentaries were probably passed down in a written tradition, but subsequently when the primary texts were started to be passed down in a written fashion only.
Good evening, sir. My name is Vipul Tiwari. I am a MA Economics student here. You have talked about wages and price discrimination.
Price determination.
Yeah, price determination.
Yeah.
I am interested to know that in today's economic system, what we have learning, the theories, actually those theories are much more applicable on the European economic system, not Indian economic system. So my question is that is there anything which we study like past economic I want to know, is there anything which is useful today if we learn something, the economic system of the previous Indian history? So as a student who doesn't know Sanskrit, what are the texts, if you can get references, and how we can start learning?
So generally the first text when we talk about economics which everyone recommends is the Arthashastra. Arthashastra has a couple of very good English translations available already, but it is more a text of statecraft. It does certainly discuss economic concepts as well, immigration, various other concepts are there in the Arthashastra. Some work has gone, the number of scholars have worked on Arthashastra, but I guess there is much more to do. Arthashastra itself doesn't claim to be the originator of these ideas. It quotes many ancient scholars and texts, and it quotes them, it either accepts or rebuts them. So Mahabharata itself is said to contain a lot of discussion on statecraft and economics and things like that. So it's not exactly my area of expertise, so this is how much I know.
So I am Pranav from CS22. So my question is basically related to the present scenario. That is basically the most of the science and maths we learn is Western, and what is being taught is also Western. So most of the progress is also happening there. So how will this Indian pedagogy be compatible with that? And is there any chance of it being compatible with the current Western kind of education which we see, especially in terms of science? And the certain terminologies which they use and certain, let's say, innovations which they came up with, are there any equivalent terms at least so that we can use this pedagogy?
No. So see, so that has to be, we have to think about how to go about it. Okay, no one is suggesting that let us do exactly what was done in the Leelavati or some other text. We certainly have to adapt it to our present requirements, and perhaps we'll also have to see. We may have to come up with various texts in various languages, because Sanskrit only few people may know. So that is one aspect of it. The other aspect of it is we can certainly expand. We can come up with terminologies. There are various countries which actually mandate translating the technical texts into their local languages and teaching in the local language. In fact, even the government of India is doing it currently. And there are professors, there are faculty in IIT Madras who have started offering courses in various Indian languages, not just English. So, and as far as the poetic pedagogy is concerned, that, in my opinion, it is very, very beneficial. Perhaps, certainly at the school level, we have to explore whether it can be something which can be applied at the college level as well. But certainly at a, the junior school level can certainly be there. And it ultimately comes down to the creativity of the teacher and the writers of the textbooks. So that's where I see the bottleneck. Yeah.
Thank you, sir, for addressing the queries placed by the audience member. I request Professor Jyotirmay Tripathi ji to present a token of gratitude and appreciation to our chief guest. Thank you, Professor Jyotirmay Tripathi ji.
So, I would like to express the heartfelt gratitude to Professor Aditya Kolachana ji for his captivating lecture on the history of exact sciences in India. Mainly focuses on astronomy and mathematics. And Professor Kolachana, your insight gave us a glimpse of a scientific heritage of scientific heritage of our nation. And we are thankful for your dedication in bringing this topic to us. We will surely research more on this. And your lecture gave us left lasting impression and inspiring us to explore the history and culture further. We hope to see you all in the next event very soon. And those who are interested in volunteering and receiving the updates further such events, please mail us on Vande Mataram @sml.iitm.ac.in. So we have come to the end of the program, but it wouldn't be complete without singing our national anthem. I would request all of you to rise and sing the anthem with us.
Janagana Mana Adhinayaka Jaya He Bharat Bhagya Vidhata Punjab Sindh Gujarat Maratha Dravida Utkala Vanga Vindhya Himachala Yamuna Ganga Uchchala Jaladhi Taranga Tava Shubha Name Jage Tava Shubha Ashisha Mage Gahe Tava Jaya Gatha Janagana Mangaladayaka Jaya He Bharat Bhagya Vidhata Jaya He